um, of scalar and vector quantities. And for these, um, it's a long unit, so it will be broken up. Or you'll have to break it up, just pause and record where the video ends and things like that. Or where you're going to pick back up. So the first part here is just defining vector and scalar concepts. And there could be up to 3 parts to a measurement. The first part is the number. The second part is the unit. Every measurement should have a number and a unit, but some also have a direction. The first 2 parts are linked together. Every number should have a unit, and we call these the magnitude. The last part is direction. The number by itself, just number 1, the number doesn't make any sense. If someone told you that you look like you're about 3 tall, that sounds strange. But 3 feet tall, then you'd realize they're just making fun of you. And that's not very nice. So they need the unit along with the number. If a measurement can be explained fully with magnitude, it's called a scalar quantity. For example, 3.2 kilograms. Okay? We don't need a direction with that. But many measurements do require direction. So we call a vector quantity as full definition requires both magnitude and direction. So in that case, we might have like the number 5, the unit kilometer. 5 kilometers makes up the magnitude portion, but we might also say east to define direction, or an angle 20 degrees. And for that, though, we need a scale of where it is. So what are some of these notations? Well, for scalar quantities, for just a scalar quantity, we would just use its letter, like A. This is the scalar quantity A. Units and magnitude. Units gives you the magnitude of that. For the vector quantity, we would use something like, well, what we would use is A with an arrow over it. And that's a vector quantity. The arrow represents the direction. So you have magnitude and direction. Sometimes you're interested in only the magnitude of a vector quantity. In that case, you put your vector in between two absolute value like symbols, two bars, and that means magnitude of a vector quantity. So that seems like the same thing as a scalar, but a scalar, remember, is defined entirely by just the number in units. A vector quantity is defined entirely by number, units, and direction. And sometimes we're only interested in the number in the unit or the magnitude only of the vector quantity. Let's look at an example with position, displacement, or position, distance, and displacement. Okay, so where something is tells us its position. Okay, and since these objects move around in space, position's symbol is just S for space. And so, for example, we could define, here's our origin. It's a little weird with the blue lines behind it, but focus on that. So here's our origin right there, and we could have something out, say, here. That would be the position. What is the position of blue? Of the blue dot. And the position would be 4 units in the x, 1 unit y. Now what if this dot changes its position? Say up to there. So now it's no longer there, but it's moved. From to the new point there. Now in that case, so we know what S is here. S is 4 units in the x, 1 unit in the y. But what we're interested in is delta S. What is its change in position? Delta means change or final value minus initial value. A change in value. So it would be S final minus S initial. And the x would have changed by going from 4 to 6. So for x, we would get a change of positive 2 units. And for y, we would have a change of, the same. positive 2 units, going from 1 to 3. So these are actually both scalar quantities still, because we're not talking about direction. Just position is 4 units, 1 unit, 4 units in the x, 1 unit in y. Change in the position of x was 2 and y was 2. But imagine you were told you're standing in the middle of a gym, right? So here's your gym. And you're standing in the middle right here. And your gym teacher says, move 10 meters. Well, if 10 meters was equal to this line, right? Then we can move out 10 meters. Well, let me put this on. We can move out 10 meters this way. We can move 10 meters that way. We can move 10 meters that way. Or we can move 10 meters that way. 10 meters. Anyways, you get the point. It's on this circle, this 10-meter circle here. Somewhat of a circle. And you end up in a circle of 10-meter radius. Your change in position would still be 10 meters. Okay? But now say you receive the direction to walk in that gym 10 meters east. Well, we still have our scale up here. That's 10 meters, and if we put on the scale north, east, then 10 meters east would be like that. Now we don't have just a change in position, but we actually have what's called displacement, which is a vector quantity, and it looks like this. Delta S, but the S has an arrow over it, and this is called displacement. And in this case, it would be 10 meters east. We've changed our position, but we've changed our position in the direction east, 10 meters east. So displacement is a vector quantity. What is your change from where you started and in what direction? Change in position is a scalar quantity, how far something travels. So we call this our distance, how far something travels. How do we represent vectors graphically? We need a scale for that. And we need to draw the length. We can draw vectors by arrows, okay? And I'll keep it simple with how I normally draw them. So like that. The length of the arrow, including the head, represents the magnitude of the vector. The direction it points represents its direction. The way the arrow points represents the direction of the arrow, the direction of the vector. To do this, we need a scale and coordinate system. Sometimes the coordinate system is as simple as plus minus in one direction, the positive way or the negative way. Sometimes we use north, south, east, west. Other times we use angles to represent direction. Okay, when you add scalars, for scalar addition, just add quantities must be like units. For example, if I walk 3 meters, 2 meters, 5 meters, I walk a total, my change in position or my distance would be 3 plus 2 plus 5, or 10 meters. Vector addition is a little different. In general, they do not add like regular numbers. They can only add like regular numbers if they're going in the same direction. Okay? When vectors are added, we call the sum the resultant. Another useful idea in vector addition is also what's called the equilibriant, and this is what you would sum, what the resultant plus the equilibriant gives you 0. So if you had R, which is our resultant, and you sum the resultant plus the equilibriant E, you get 0. So this equilibriant is same magnitude but opposite direction. Then the resultant, and it results in giving you 0. Okay, let's look at graphic addition of vectors. Graphic addition of vectors. If a set of vectors all drawn to a scale with reference to a common coordinate system can be added graphically. Okay? The tail of the first. Now when we have a vector, let's do that. So say here's a vector. We call this the tail, and we call this part the head, okay, of the vector. The first, when you add them, the tail begins at the origin. So drawing or graphic addition of vectors. Tail at origin. Connect subsequent vectors. Heads. Head to tail of new vector. Resultant is the vector from the origin to head of last vector. We need examples. Let's say we're given the scale. We use a simple XY scale, like that. And 1 centimeter equals 3 meters. And let's say we have vector A. That looks like that. We have a vector B. That looks like that. And we're given AB, and we're also given a C that looks like this. Let's find the resultant, R, which equals the sum of A, vector A, plus vector B, plus vector C. Now, if I start with A here, it would be at my origin. So if this is where I start, clone A, you could redraw with your ruler and protractor, in case it's going that direction. So I have E, A. So to redraw, let me say, because, I have a clone function, you don't. So, well, you might not. You might, I don't know. So if 3 centimeters was equal to, now this obviously is just a ruler that it's not actually centimeters, but if I treat it as a centimeter one, I could see that A is about 4.3 centimeters, which I could convert to meters, but right now I'm just going to put it on, and I would come down here to start, and then I would go 4.3 in that direction. Now B, I would see is 2.6 centimeters, and it has a direction of, if I put the center crosshairs there, extend the ruler along since it's already there, at 42 degrees. So if I come down here, I would draw my vector B starting here at 42 degrees outward. So in this case, I'm just going to clone it. That's how you would do it, to move and draw that. And notice I'm putting it from the head of A, the tail of B on the head of A. And now I would measure C and use my protractor again, but I'll just use the clone function. If I can find it, here it is. And I would now put that on the head of B, the tail of C. I'm going to move all this down a bit. I know it's easy for me to do that and hard for you, but there we go. And now, remember the resultant is the vector from the origin to the head of the last vector. So a resultant here would go from here up to there, like that. Now this I do have to measure. We'll call this R, the resultant, because I can see, first off, I measure the length of it. Get that on there, right? At about 5.6 centimeters, okay? And then that 5.6 centimeters, if I convert it to meters, unit conversion, 1 centimeter by this scale is 3 meters. So I would have a magnitude of 5.6 times 3, or 16.8 meters. Its direction is in the XY plane. I can use an angle from the x-axis. Actually, I'm going to change from XY here to, a theta angle. The theta meaning angle. Or let me just use an angle symbol right now. Angle. Where this is 0 degrees, this is 90 degrees, that's 180 degrees, and that's 270 degrees. So I can see mine is, if I start there, put that on the origin, 10, 20, 30, 40, 52 degrees. So at 52 degrees. That's my answer for my resultant sum of these vectors using a ruler and a protractor, and that's called graphical vector addition. Okay. Just for a point, if I took A, B, and C and rearranged them, so say I did B plus A plus C, does that still equal R? Should, right? If you're summing 3 vectors, the order shouldn't matter. So we started with B, so that's now going to start at our origin. We'll need A. Give it a try. Okay, good. Hopefully you had B plus A plus C. And remember, you start at the origin and go to the head of the last one, like that. And you could see that this resultant is very similar to, well, it's the same, but I did it graphically, so it's hard to see exactly what they match up. So order of summing doesn't matter. equilibrium of R here, if I drew that, it would look like that, because what this is the sum R plus E would give 0. It would bring, so whatever, it's equal in magnitude, opposite in direction. So this here is the equilibrium. And remember, R plus E equals 0. Same magnitude, opposite direction. All right. Now, what would be the direction? Whoops. Oops. Sorry. What would be the direction of vector C? If C is like that. Do we say northeast? If we said northeast, well, what about this vector? What about this vector? Which one's northeast? Which one isn't? Well, that's where the angle system comes in that I just mentioned earlier, but you start at the x on the x-axis and our y-axis. You're starting at 0 degrees, 90 degrees, 180, and 270. This would be 90 degrees, okay? A vector, say, like this, that would be, say, around 120 degrees. So a vector like this is 0 degrees. A vector like this is 90 degrees. And a vector like this is 120 degrees. Okay? Let's add some vectors graphically. Okay? Here's an example. Okay, so let's say at 10 units at 20 degrees. You had 20 units at 180 degrees. Well, do one black, oops, and one red. 20 units at 180 degrees. Okay? And let's say 1 centimeter equals 5 units is our scale, and we would draw on there an x, y, 0 degrees, 90 degrees. It's letting us know how the angle system works. I'll get my ruler out, my protractor as well. That over there. All right, so if 1 centimeter is 5 units, the first vector that I'll add is the black one starting. I'll have a origin, say, of right here at the start of my ruler, and 10 units at 20 degrees. So we bring this over, line up that, and mark off the 20, 10, 20 degrees. Okay? Now, 10 units, if 1 centimeter is 5 units, it's going to be 2 centimeters. So I'm going to put that, and I'm going to see I didn't bend it enough or too much or whatever. I want to get them aligned, and then 2 units, or 2 centimeters, 10 units, would look like a vector like that. Okay? So there's my first vector drawn. Now, I'm going to do the red vector. Let's call this one A, by the way. So that's A. Let's call this one B. And we're going to find R, which equals A plus B. Now A is drawn. B has to be connected head to tail. And that's 20 units at 180. So at 180, it's going to be straight down. So put my protractor on the tip. The crosshair's right on it. And I got to bend this over. Go straight down like that. I can move the protractor around too, if I make it easier. I got to take this off now, though. Put that back on it. Okay, so now how many units here? So 20 units. 20 units is, if 5 units are 1 centimeter, 20 units is going to be 4 centimeters. So the red one, B, is going to be 4 centimeters down. Like so. Okay? And now I've drawn my B in. And now I have to draw in R. If I draw it first, I know I start at the origin and go to the head of the last vector drawn, which is B. So, I think I had it blue, didn't I? Yeah. So, starting here and going down to, and I can see I have 3.7 centimeters. Okay, well, I need to change that because remember my scale up here is 1 centimeter is 5 units. So 3.7 centimeters is 18.5 units. So my resultant has a magnitude of 18.5 units. But what is its direction? Well, that's where I take this over, and I have to use a little creativity here, okay? Or just some thought. So this is 0, this is 90, this is 180, that's 270, right? So this, with this flipped over, that's 270 right here, and then that would be 280, 290, I'm right at 300. So my direction is 300 degrees. And there's my graphical sum of the vectors A and B using a ruler, protractor, and appropriate scale. Well, that's the first part of 1.4. We'll come back to part 2 later.